So we're happy to have our second speaker for today, Pavel Panteleev, who will tell us about the mathematics of bad LDPC codes.
Okay. Hello everyone, can you hear me? So at the last moment I made a change to the title, so the title is The Mathematical Theory of Really Bad. Okay, and so first let me just remind you what do I mean by code before I say why I call them really bad. Okay, so let us first start with classical codes. Classical codes, I think many of you know this definition. I just fix some notation here.
Maybe take a bit of pen.
Oh, yeah. Okay, maybe this one. Okay. Okay, so, no, this is not that.
Oh, there are lots of them on the other side.
We took the blackboard away. I'm sure. I mean, I beg you.
Okay, so the code, by code I mean linear code, so it is defined by some parity check metrics, so it's a kernel, standard definition, and so we have the dimension, as usual denoted by k, and we also have the distance, which is the minimum having weight of non-zero code. Okay, and so today I will speak about LDPC codes, and it is really beneficial to think about them in terms of graph, so-called Tanner graphs. So this is a bipartite graph, which is constructed from parity check metrics. So you have the rows, so the checks, and you also have the bits, and you connect the bits and the checks. And we consider LDPC code. By LDPC code I mean an infinite family where we all this graph has bounded degrees. And it is also beneficial to think about codes, even classical codes, as a chain complex. So it's a length one chain complex that consists of two terms. Okay, so the matrix H, so we apply matrix H, and the kernel of this is our code. And so LDPC codes are ubiquitous. You can find them everywhere in 5G, Wi-Fi, whatever. And if you look at specification, so of course I believe almost everyone here are aware about so-called good LDPC codes constructed by Sipser-Spielman. In fact, Gallagher also constructed good codes, but they were not explicit. And but if you look at the practical codes, the actual codes that I use in practice, for example, the ones that I use in Wi-Fi that we use here, for example, then you will see that they are constructed in some very special way, and I will try to explain you why, what's the reason why they constructed in this way. So, and for this I need a notion of a lift of a graph. I believe that, so by L lift in this talk, so I just mean, sorry for the people from pure mathematics, so by L lift, so I'll apply this short term for L-fold or L-sheeted covering. So it's just some term that is commonly used in graph theory and also in the field of LDPC codes. And how we, why it's so important? Because in this way, so this L lift, it can be described in a following way. So suppose we have some small base graph, and let us assume that so we have darts, yes, so we have edges in all directions, and so we can define a function where f, so it's a fiber, it's some small set, and not necessarily very small, it's just some set of size L. And as usual, so we assume that if edges are, have different directions, then these permutations are how to say this? They are mutually inverse. Yes. Sorry. And so let me just give you some example, because this would be a good picture. Okay, so let us assume that we have this very simple graph, and so let us assume that f, in most cases f is just a group, and these permutations are just regular actions, left or right. So let us denote the base graph by B, and if we consider L lift, yes, we get a large graph where we have these fibers, and so each fiber, for example, we consider 3 lift, and so let us assume that we just randomly assign some numbers here. So it just means, so here we have just direct connection, so here we have a connection by 1, shifted by 1, and we also have another edge, yes, and so which means, so it's, we have so these connections, and here we have, oh, sorry, this is not 0, this is 1, okay, and here, so here we are done. This is just, you have some mental picture, so we can represent it somehow. And we denote this lift by B lambda. So in the case when this is a group, yes, so we can represent these larger graphs and larger codes. So in this case, we applied it to code, yes, defined by this graph, and from using this operation, we obtain a larger code. And so the main idea of this lift is that we start with some fixed small base graph, and then we construct a family of different codes. For example, in 5G, so we have just 2 base graphs, but we have like almost hundreds of different codes that obtain just from 2 graphs. And this is very convenient because so you can describe it in a very simple way. And it's also, there's another very important reason why so we start from 1 base graph. Because these base graphs are usually not just arbitrary. So they are chosen in a very specific fashion. So the way practical LDPC codes I used, so usually, so we are really concerned about distance, yes? But the LDPC codes, practical LDPC codes, are decoder oriented construction. So it means that they comes with some special decoder, and the code is constructed so that this decoder performs in an optimal way. And there is a theoretical analysis that allows you to look at this base graph. And in fact, what people do, they consider its universal cover, and they kind of try to run this decoder on this universal cover, since it doesn't have cycles, so you can have very good analysis, which is very precise. And then they apply it to these lifts, which do have cycles, yes, but when you construct these lifts, so you try to avoid short cycles. So these lifts, they look like the universal cover of this base graph. So this is one of the...
In a way you cannot avoid short.
Yes, of course, you cannot avoid.
Really short, like logarithmic.
I agree. And the reason, so in what people do, they try to, for the given length, so if, for example, you want to construct a code of length 1000 or 2000, they try their best to avoid small dangerous cycles. This is the main idea. Okay, so I explain, I think I explained why people use these graphs. And next, I would like to say about what properties we have from this construction. In fact, using this idea, so we can obtain good codes without any problems. For example, if we start from...
Not good in the way we define good.
Yes, in the way we define good. Exactly, in the way we define. Yes, linear.
You can get good.
Yes. Just by using this simple idea. Let me explain how to do this. And it's quite simple. So we start from complete graph, and we apply just random lift. So here alpha is, so we assign to each edge a random permutation, just random permutation. And it is shown that with high probability, this has distance that grows as the size of the fiber. So if we increase the size of the fiber, yes, so linearly, for example, then the distance also grows linearly. And what is important, that you have full control of rate. Why you have full control of rate? So the rate of the code, let me define what it means. So it's k by n. And what we need to construct good codes, so we need a family of infinite codes that has rate that is not vanishing, and that has distance that also grows linearly. And in this case, when we apply a lift, so we always guarantee it, so it really doesn't matter which lift you use. For each of them, you get very good rate. And this rate is at least, yes, so it's, let me maybe denote this by C, because it's a code. So the rate, the dimension of this code divided by the length. So length here n different n, so let's see. So it's at least 1 minus mn, and this is because so it's guaranteed that the number of checks and the number of bits grows linearly. Yes, and
Since
so we have the same proportion. Yes.
Yeah, since you're talking about practicalities, I'm curious why, I mean, not for this local checking, but why are GOPA codes, are they used? GOPA codes.
GOPA codes.
Are they used?
They're quite
Is there-
short. They're quite short codes usually. You mean if you mean by Gopher codes,
'cause they beat Gilbert.
the whole class of algebraic geometry codes. The problem is that this is exactly the problem that I pointed out. That LDPC code is a decoder-aware construction. So it's a construction specifically designed to work on on the decoder that comes to it. With Gopher codes, we do not have very good and fast decoders, and this is the main issue. Of course, if we would have such decoder, Gopher codes will win without any problem. But what is important about LDPC codes, because their decoders are usually linear. Yes, they are sparse codes, and the decoding, the complexity of the decoding is proportional to the number of edges, multiplied by the number of iterations. But usually you fix this number of iterations, so it's proportional to the size of the graph. So it grows linearly with the lift size.
Can you please explain again how you get the code from the graph?
Okay, so the code is just a way to represent the parity check matrix. So the parity check matrix is a linear operator, yes, and it's a matrix. So it has some rows. Here's the rows, and it has some columns. Here's the columns, and we connect a column with a row. We have one in it. So we can see the binary codes today for simplicity. Okay. And in this way, so we can just consider bipartite graph as a codes, yes, and we can talk about them as a codes. But we also need this notation, this notion of the weight matrix, which is also will be important for our discussions. So in this case, so the weight matrix, it says how many parallel edges we have between between bit and the check. So in this case, so it's will be so we have 2, 1, 2, 0, because we do not have checks here, and for the second row we have 0, 1, 1. Yes, this is what we will call. In fact, this weight matrix, it completely defines this bipartite graph. So it's just another way to represent it. Okay, and what is also interesting that this lifted graph, when we lift using regular coverings, so it can be also considered as a code with parity check matrix over the ring, and this is also quite handy. So for example, in this case, so we can, this ring is a group algebra, and so here it's x, okay, x1 plus x0, and here 0, and here we have x0 and x1. And ring here, as I said, so it's a group algebra. In our case, so group is cyclic, so it's very simple ring.
What is X? The image in G.
X is a generator of a group. X is a generator. Okay, so in fact it represents a shift. So this x in the power of I, it means this how we shift it. And of course we can use arbitrary groups, abelian, non-abelian, so just for simplicity I consider this one. And in fact in practice people usually use only cyclic groups, and that's more than enough. Okay, let me, okay. And now let us us consider only abelian lifts. Yes, as I said, so in practice, people usually use cyclic lifts, but for generality, let us consider abelian lifts. And what is interesting that in this case, we no longer have this result. And this is exactly why I called, why I changed the name of my talk. So the mathematics of really, really bad, so I changed it again. Really, really bad LDPC codes. And by this I mean, so we have the following simple result. So first let me say that, let me say that alpha is abelian, so it means that if we consider image of this alpha and generate a group, then this group is abelian. So it's very natural definition. And for abelian alpha, we have the following result, that the distance of the code defined by infinite family starting from the same base graph is just a constant. So we are talking, that is why we are talking about really, 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 really bad codes. And okay, but still they are used in practice. And today, so when we use Wi-Fi, you use this kind of codes, and this is quite interesting. So, and one of the reasons why distance is not the ultimate answer, so consider this picture. So when you transmit a signal, yes, you have random errors. And if your code has minimal distance, that it means that in some cases, yes, you will have a problem when you hit this particular low weight code word. But if the number of low weight code words is quite small, then this is a very, very rare event. And this is one of the main reasons why codes with very poor minimum distance can still be very excellent in practice. Yes, and in fact, they perform better than GOPO codes, for example. They have or BCH codes that have much better parameters.
But excellent means that actually percentage.
For example, I can give you an example. SSDs, yes, solid state drives, up to maybe 2000 or approximately, people use only BCH codes to protect information SSDs. But then they switch to LDPC, and exactly from this family.
No, but I'm asking for random errors. Would you expect a percentage? Just for random, not the distance.
Percentage? What percentage?
Like a fraction.
The code from a
constant fraction?
Oh.
Fraction for random errors?
Yeah, they can even if, for example, have distance like 10, they can easily correct 100 or 20 errors,
Yeah.
and even outperforming BCH codes, because BCH codes has bounded distance decoder, so they just, yes, they of course this is ideal in some sense decoder, but one of the main problems is BCH, not only that they have bounded distance decoder, but also LDPC codes can also use some what is called soft information. So when you receive signal, you do not receive 0 or 1s, you receive some scale, and they can easily adapt it. But for BCH codes, it's very, very hard. And this is also one of the main reasons why LDPC codes are used in practice. Okay, and for this result, so it has quite easy proof. So it's not that hard. So you can just consider this lift. And then, since you have a abelian group, it has very bad expansion, yes? And in fact, you can find a small subset set A, for example, in the group G, such that SA, and I'll explain in a minute what is SA, is smaller than 1 plus epsilon A. And by SA, I mean, so I consider all these shifts that I have, yes, and consider them as generators. I also consider the inverses, and also add the identity, and so we have like a symmetric set of generators. And since it's a abelian group, so we can make this epsilon arbitrarily small. And we can, in fact, make it small, like, for example, n minus n minus 1. And in that case, you have a problem, because you can consider a code where we support it only in these subsets A that I chose. And here, I will only touch syndromes, only touch checks that from this set, yes? So all my checks could be only from this set. And now, what I can do, I can consider like a new code, yes, so new parity check matrix that is restricted only to this A and this SA. And since, so from this equation, so we have that NA is more than SA. M is the number of vertices here, and n is the number of vertices here. Then we see that so it has some non-zero code word, yes, because this we have small number of checks than the number of bits. It's a very simple argument. By the way, it also works exactly the same for quantum codes. You just need for quantum codes consider another checks and do absolutely the same. And here just use mx plus mz. Okay, but okay, now we know that these codes are bad, but we do want to know how bad they are. And this is a natural question for a mathematician. And so we can define.
Is the lack of expansion is the only reason for being not good? If I will tell you that I'm taking the group G to be expander and generating a expander, then it automatically, the computation like with the random still work to get linear distance.
So if it's non-abelian, if it has a good expansion, then I expect that they may even have linear distance. So if the group is non-abelian.
So it's a proof or just there is no counterexample? One can really make it.
So in fact, you can do the same type of arguments for non-abelian groups. For some non-abelian groups, if J is constructed with finite number of iterations and as extensions, but but in general, I assume if you use a simple group here, so we cannot have such argument, and I expect that they could be linear distance code, but nobody knows the proof of this. So we do know about some constructions, not this kind of, not random, yes, not random assignment, but some specific constructions that give good codes. So it's possible. Okay, but I need to define a value. So since we have this problem, yes, so we can define the value. That is equal to maximal distance of the codes that are constructed as abelian lifts we know that if for a fixed base graph, it's a constant. But what's this constant? So let us denote it by DAB. And this is a place where the fun in mathematical part starts. Okay. How we can find it? And here, so first of all, the first result. So I'm going to present that this value. So here I just I look at all possible abelian covers, yes, but I can restrict.
Please change the marker.
Sorry, I'll change the marker. Okay. Sorry. Okay. Okay. So the first thing that I should say that this is exactly the same. So this is the first result. That if I just replace here abelian by cyclic, yes, if I restrict to cyclic groups, then nothing changes, and this is also maybe quite surprising because we restrict the groups, but we do not lose anything. Of course, we can lose in the size of the group, yes, that achieve this bound, but we do not lose this number. Okay. But we are interested in this particular number. So how one can find it? So in order to find it, so it turns out that this idea is related with so-called universal abelian cover. So we have universal cover, yes, but of course if we are interested in abelian covers, it makes sense, yes, to consider universal abelian cover. So let me briefly remind what it is. So I'm not sure, maybe everyone knows.
We're all physicists, we all know block wave.
Okay. So we denote it by BAB. So it's some particular indefinite graph that is defined as the set of. So we take paths that starts. In our case, so when we consider base graph, so we consider only connected graph. Yes, I forgot to say about this, but we consider only connected base graphs. So in connected base graph, so we can choose one vertex, and starting from this vertex, we can consider path.
Do the lifts need to be connected?
Sorry?
Do the lifts need to be connected?
Lift?
Yeah.
No, not necessarily. P starts in A, and here is so we also if we consider universal cover, yes, so that we just need to say that this path is irreducible, and that's fine. But for abelian cover, so we also need to define some equivalence relation. So we say that two paths are equivalent if they end in the same vertex, and if this is the most important condition, if you take the path P and the reverse of the path Q, then in this path, so I call it H neutral. So it means that how many times we go in one direction, the same number of times we go in the opposite direction. So it means that it's a closed walk where we go through each edge in the right direction exactly the same number as in the left direction. So for each edge. Yeah? Is it clear? So this is how we define it. This is of course an equivalence relation, and this equivalence classes are our vertices, and we can also of course define edges so append just to the path some edge, and so that way we have edges in our infinite graph. But in fact, there is a little bit nicer way how to think about this graph is just to consider the first homology. So if we look at the graph, yes, and consider its space of cycles, then it has the rank which is equal to okay, and in fact you can view this graph as a covering with this group. Yes, and why so? Yes, because when you so this condition that I explained to you is exactly the same as if I say that this one is equal to 0 in this homology. Okay, and in fact, I think the most interesting way how we can view this is to take, since every lift, as I just explained here, can be explained as a code over ring, we can also consider this code that corresponds to this universal abelian cover, and this code have let us be specific and maybe just consider graph K 2, 3, yes, and the matrix, if we define the matrix, the corresponding matrix to this code that corresponds to this graph, then it can be described in this way. So here, so we have how can describe? You just take any spanning tree, yes, and in this spanning tree, so you fix this to identity, and all others, so you can change, and this is. So in this language, it corresponds that here we set ones, and we have only 2 degrees of freedom. Yes, and you can see that the B is equal to 2 in this case. Okay, so and we can describe, so we can consider an infinite code that is defined over this ring F2. And so how it's this code defined? So it's just a set of, for example, in this case, vectors. Each component is from this, and that give you 0. It's a code. But in fact, you can even describe it in even nicer way. So we can consider, instead of this ring, maybe it's not very convenient for everyone, so it's much easier to work with polynomials. And in fact, you can just replace it to a ring of polynomials, and you can introduce the polynomials for each edge. Yes, so it means that we okay. And now, so we change the ring. It's a ring of polynomials. But the distance of the code, so we are interested in the distance of the code. Distance of the code is exactly the same, because so what we do here, so we just multiply by some monomials, and so we do not change the distance of the code. And we will work with this graph. So and so the first immediate result of this is that so it's not very immediate. In fact, the first result, and it takes some time to prove this, that this d abelian that we describe in here is exactly the minimum distance of this. Let us denote this by h. Okay, so it's exactly the minimum distance. So this is like the first meaningful result. And now, so we can play with it. So how we can estimate? So given a graph, yes, given a matrix, how you calculate this? Is there any efficient way how we can do it? Because this definition is not very good because we can see the infinite ring. And it turns out that in some special cases, so you can do this, and so I still do not know the answer in all cases, but in some special cases it's quite nice, and these cases are very relevant for applications. So, for example, in this case, it's m plus 1 factorial, and it's only if n more than n.
You're
So
looking at the maximum abelian cover, right?
yeah, maximum. Yes. And so in other cases it's infinite. And by the way, here the proof is not very elementary, so it's might maybe look simple, but now so you need to work with polynomials, yes, and somehow to describe their code works, and this is an infinite code, so you cannot just as for finite codes, yes, we can just enumerate and just say something here, so it doesn't work. And so it means that we also, it's also interesting what bounds we can have in general. So it turns out that this idea, of course, is related with the girth, but with the girth of this universal abelian cover, maximal abelian cover. And in fact, it even has a special name, so it's called abelian girth. It was studied in some papers even. As far as I know, it's the first who considered it was Joel Friedman in his work on chiffon graphs. And so the definition of this girth is simple. So it's just the girth in this universal abelian cover. And so there is a natural connection between the girth and the code, and it is very well known, yes, in coding theory, that if we have a graph and it has some girth, so you can give a lower bound on the minimum distance, and so the idea is just you take a vertex, then you have some, for example, d edges, then you have checks, and if you have one here, so it means that all these checks are unsatisfied, then at least one of these also equal to 1, yes, because it's unsatisfied, and then you can go more and more. So it's so I do not write the formula, but so you get the idea. So sometimes it is called Tanner tree bound. So in general, so we have this lower bound. But many, in fact, much more interesting are upper bounds, because they are upper bounds for all the codes. And in this case, so maybe I can just use. Okay. it turns out that this is also related with permanence. Let me explain the connection. So let us consider our, maybe I, just because I need this example, but I can write it here. So let us consider our example. Okay, so this is a graph K 2 by 3, and if you okay, can someone say me the girth, abelian girth of this? So the girth is obvious, but what is abelian girth? Is it obvious or not? Any? Okay, so the abelian girth, so how we can define in easy way abelian girth? So abelian girth is the smallest non-reducible, non-backtracking loop that has the same number, so it goes the same number in each direction for each edge. Yes, so it's a special loop with a special property that if you go in one direction, so you go the same number in the different direction. So we just restrict to these loops, and we consider only these cyclic or non-backtracking loops. And here, if you look carefully, so you can see that this guy has the loop of length 12. 12. And so you can just go here, 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 and so if so this
why is it not shorter?
and that's a good question, by the way. That's a good question. And so this is related with a general bound. There is a general bound that if we have a graph, then its abelian girth, it's at least 3 times the standard girth. But this guy has girth 4, and so it has at least girth 12, and we already know this girth 12. But why is this girth 12 also important? Because when we travel against this girth, we also can construct a code word for this infinite code. Because so we participate here. So in each vertex, we will in this walk of length 12, we will have 2 times. We will hit 2 times. So it means so it kind of so we can construct, if for example here we take identity group element, then when we next time we have some another group element, and so in each case so we have 2 group elements, and their sum is so if we took their sums, then it will be code word, because everything is connected in the correct way.
The
And
3 has to do with the graph being 3 regular. What's it?
no, not 3 regular. So it's
No, why? Is that always 3 then?
yeah, it's always at least 3.
Oh, at least.
At least it's not equal.
Oh, yeah,
It's not
okay,
equal.
3 at least.
It's at least 3. So in fact the answer, the general answer for this, if we consider the general case, so this is only 12 if our graph contains this as a subgraph, and in all other cases it's indefinite. And so we can just by the way, everyone see why, for example, this guy has indefinite, because it's just so it's just a line. Yes, it's abelian, universal abelian curve is just a line, so it has infinite girth. And why is this important for applications? By the way, this number 12 was invented by coding theorists first, even before all these papers on abelian girth, because they were interested. So when they construct this abelian graph, they were interested to what girth you can lift the graph. Yes, and there is a limit. Yeah, if you have if your graph, you have subgraph k to 3, then you cannot lift arbitrarily. Yes, you can only lift up to 12. So it's a little bit frustrating, but not a big problem. And of course, this is important because you cannot, for example, apply these other ideas like, so if girth is bounded, that it's not very good. Okay, but I suppose to tell you about the general solution for this. So it turns out that we can also construct this code word in a different way, quite unexpected. So we can just consider a code word that consists of determinants. So here we have and so I think you get the idea. Yes, it's and so oh. X2, X3, X5, X6. So you just take, so the idea of this is very simple. First of all, I should remind you that we are working on over the field of characteristic 2. Yes, it's a field of 2 elements, our ground field. And in order to see this, why this is a code word, you just duplicate any of these rows. Yes? For example, and put it in the first, as the first row. And then you just calculate the determinant. And this determinant is equal to 0. And you would have these factors in this determinant. And this is exactly why, yes, you can do this for each row, for this row and for this row. It means that this vector is orthogonal to both of them. So it's indeed a code word. So we constructed a code word, and it's polynomial. Yeah, so it has finite length, and see, here I think you understand how we get permanence. Yes, because if we want to estimate the weights of these determinants, then we can estimate. So we can, for such kind of determinants, if we have some polynomial matrix, so in general any polynomial matrix, then its determinant, its Hamming weight of determinant is bounded by the permanent. So the permanent is just determinant but without sign. But the permanent of the weight matrix. And so in our polynomial terms, it just means that we kind of substitute 1 in each variable. So it's, but we consider it as an integer. So it's very important. So it's not an element of the field. So it's our weight matrix. Yes. So I mean, so here, so our purpose. What our purpose? Our purpose is to get some bound just based on the graph. This graph is defined by this integer matrix, so we want to use it. And we can, of course, generalize this to arbitrary matrix, yes, in a straightforward way. How would you generalize it? Who can say? For arbitrary matrix. What's the natural way?
When you say arbitrary metric,
So we constructed a code word, an example of code word. How we construct many other examples of if we, for example, given some general matrix, m by n matrix.
Use all the minus.
Yeah, so the most straightforward way that people tried is just take this m plus 1 and any m plus 1 rows and do the same. So we kind of put zeros here, and so we can see like submatrix. And if we do this, then we get the following well-known estimate in coding theory. So it was discovered absolutely not related to this abelian distance, so this is a new notion, so it's not the same thing. But using this, we can get the following general bound. So it's so the idea is that we take all possible subsets J, yes, of size m+1, and for each such subset, so we calculate the sum over OJ from J for this permanence. So we just, so each permanent give you, so here we can see the submatrix. So here we take all rows, but we take J minus J. So we remove each column. So we take the subset J and remove each column, and this sum gives you example of cold word. And here this mean star means that we consider only minimum of expressions that are not equal to 0. Of course, if we have a 0, that's not a good example. And this is a very well-known method from was applied to quasi-cyclic codes. And what is interesting is that it turns out that it's very far from optimal. So the first, so you could think that maybe this is the same, but in fact it's not the same, and I can show you that the difference is huge. It can be really huge. Okay, so if we, for example, take such weight matrix, then if you try to apply this idea, then this bound, yes, and you get 36. But the real distance here is only cold words. Okay. It's only 6. Only 6. And who sees this? Why it's 6? Maybe somebody see this. So here, so the secret is here. So we of course, this is a connected graph, so this is everything is fine. So, but here we see that we have this part, and we can try to force, for example, here all zeros, and try to construct example here. And this is a very simple. And here you can have this kind of example like this, and it's 6. So we know that the answer is 6. But this formula predicts incorrect value. So so let me show you some possible correct values that I conjecture that it's the correct one. At least all my tests and show that. So in all experiments, so you can calculate it efficiently. So it exactly corresponds to the correct value. So if we define a modification of this, so for this modification we just need to work on this counterexample. So we consider this subset G, and we consider also subset of rows also, which we didn't do before. And what we do, so we call a pair I and J admissible for this matrix if we have two conditions, very simple. This one, so we define this value. So J, large J and small j. So in fact, so this value is, just try to construct counterexample for this submatrix. The second condition is that so we still, yes, if we construct a counterexample for this submatrix, it doesn't mean that it's the counterexample for all matrices. We need orthogonality to each row. And for this, so we need some different condition. So we just require that the permanent of this matrix I with edit I and J is equal to 0 for each I that is not, so for each row that is not part of this row, so we require that kind of this, so this guarantees that we have orthogonality and the correct code work. And this one seems to work, and I even have a proof for the case when we have matrices where n equal to n plus 1. So I have a proof in the general case that this is the correct value. But in general, so this problem is open. So I think I can start here. So maybe just write a conjecture that maybe this is the same. Yes, and also, of course, I do not have time to speak about quantum codes, but it seems like that for quantum codes, so we also have some similar idea, and so we at least we can generalize this bound m plus factorial. So it's also possible to generalize it even to quantum codes. But for quantum codes, it's much harder because you do not only need non-zero code work, but you need to check that it's non-degenerate, and it is much harder because how you can guarantee that it would be non-degenerate in all possible coverings? This is a very much harder problem. Okay, thank you for your attention.
Any questions?
I wonder about the n plus 1 factorial that you showed in the beginning.
Uh-huh.
Can you say anything about how you prove such a thing?
M plus 1 factorial. So basically, the upper bound just determinant, because if we apply here, so it's 2 factorial, because it's and we have 3 places, and so in the general case we have m plus 1 places and m factorial in each. So it's this is the upper bound, but the lower bound is much trickier, because it's very hard to do when the number of variables is more than 1, because here this technique only applies when you have when your when your rows, yes, they when you have columns. And when you have m plus 1 columns, then you can easily describe all the code words. But if you have a larger number of codes, that it is much harder problem, and it's in general it's not even clear how to approach it. So it's but it works, at least for this kind of graphs it works. So even in this case, so this is the only type of graph that it is possible to show it in general.